Before we begin learning about the actual visual field pathway, it's important for us to understand how light enters into the eye and how that light gets converted into an electrical impulse that can then be interpreted by the brain. So here we have a cut section of the eye. I'm not going to get into too much of the details of the eye, but what I will do is highlight some of the important anatomical features just that are appropriate to our video. So once you have a picture that is right in front of the eye, right over here, it enters through something called the lens. Now the lens is in charge of refracting the light. Now it refracts the light and then it brings it back and wants to focus it on this area known as your retina. Now before we get into the retina, another thing I want to mention is this part of the eye right over here. This here is known as your macula. Now the macula contains an area inside of it which is known as the fovea. Now these areas are rich in blood vessels, and also they are responsible for the 20/20 vision and the best color enhancement in our vision. And they're located centrally. So when we look at the lesions of the eye, we'll see that the macula is actually the center area of your vision. The final thing before we move on to the retina is something known as the optic disc. Now the optic disc has another name, which is called the blind spot. The blind spot is the area where the optic nerve, this orange part is the optic nerve, actually does not go inside. This is where the blood vessels enter. Now, if we take a look at the cut section of the retina, what can we see? Now the retina is actually filled with specialized cells. These cells, what are their jobs? Their job is basically to convert the light image that we have seen and turn it into an electrical impulse. So it can be processed by the respective visual cortex. Now, if we look at some of these cells that are contained inside here, we have right down here the optic nerve. Before it gets to the optic nerve, we have these special cells over here called photoreceptors. Now, photoreceptors are made up of two different types of cells. You have your rods in the blue, and then you have your cones, which have the different color. Now, the rods are responsible for black and white. The cones are the one that actually give you the color vision. Once light has been processed by the rods and the cones, they then travel to bipolar neurons, then send the signal down to the ganglion cells. Now the ganglion cells, their axons converge and form the optic nerve, which we can see right over here in the orange again. Once the image entering the eye has been processed by the cells of the retina, that electrical impulse then travels down the optic nerve and thus begins the visual pathway. So here we have our visual pathway. This, what you're seeing here, is your visual field. Now the visual field is referred to as the image that you are seeing in front of your eyes. These, of course, are your eyeballs, and then the retina in the back, through which the optic nerve goes through. So here we can say that we have our optic nerve, which we will draw in shortly. This crossing point right over here is known as your optic chiasm. And I'll explain the importance of the optic chiasm just in a bit. Any optic nerve that passes after the optic chiasm is known as your optic tract. From the optic nerve, crosses at the optic chiasm, goes to the optic tract, to this area called the lateral geniculate body. Your lateral geniculate body is responsible for then sending the action potential to the respective visual cortex that is processing the image. After the lateral geniculate body, these fibers that go into the respective visual cortex areas, they are known as your optic radiations. Now, the optic radiations, they have many different parts, but some of the parts that I wanted to go over are the outermost lateral one is known as the Meyer's loop. The middle one being your medial bundle. And that one being your central bundle. Now, the visual field can be divided into two different parts. The most lateral part is known as your temporal field of vision. That applies to the lateral side of the left eye as well. So then the medial area is then known as your nasal field. Now, in each eye, we have our retina, and the retina then transports the image to the optic nerve. As I told you before, in the anatomy part of the eye, the center part does not have, is known as your blind spot because there's no optic nerve passing through it. The optic nerves only come through each side. So we have divided the temporal, the field into the temporal and the nasal sides. Laterally, it's temporal. Medially, it is nasal. These retinal fibers can then also be divided into temporal retinal fibers and nasal retinal fibers. So now that you understand the divisions of the fields and the retinal fibers, there is a specific rule in which what happens is that, let's take, for example, the right eye. When we look at the right eye, when the image comes, it always comes in a diagonal manner. So we can say that the temporal field of the right eye comes and projects its image and its process on the right nasal retinal fiber, whereas the right eye nasal field is projected on the right temporal retinal fiber. Similar on the left side as well. The left eye nasal field will hit on the temporal retinal fiber, and then the temporal field of the left eye will hit on the nasal retinal fibers. The second rule that's very important to understand is that the nasal fields never cross at the optic chiasm. So we can also say that the temporal retinal fibers do not cross at the optic chiasm. So the pathway that these take are literally being conducted in the same direction. And then they go into the lateral geniculate body. The temporal field, or the nasal retinal fibers, however, do cross at the optic chiasm. So you can see that the red fibers have met with the red fibers and the blue fibers have met with the blue fibers. Now, why is this so special? So, everything that you see to your right in your vision, what does that include? That includes the temporal field of your right eye and the nasal field of your left eye. If you follow their tract, you can see that it's being processed by the left side of the brain. Whereas the left side of the visual field, which is your temporal field of your left eye and the nasal field of your right eye, they are processed by the right side of your brain. So it is safe for us to say that the right field of vision is processed by the left hemisphere, and the left field of vision is then processed by your right hemisphere. Now, different lesions in different areas of the tract will give you visual deformities, and we'll talk about that in a little bit. Now, where in the brain exactly are these electrical impulses received from the eye processed? So we have two visual areas in our brain. We have a primary visual area and we have a secondary visual area. Now, the primary visual area is also known as area 17. They basically interpret the color, size, shape, motion, etc. of the electrical impulse that you have received. Now, area 17 can be found in the occipital lobe of the brain. Here we have a lateral we have the lateral side of the left side of the brain, and here we have the medial side of the right side of the brain. So on the lateral side, where can area 17 be found? Area 17 is actually found in this little area here in the back. And if we were to find it in the medial side, we would find it in a line going something like this. Now the second thing is the secondary visual area. And these are areas 18 and 19. And what is their job? They basically integrate perception, so the image we've received, with past experiences. So, where can I find areas 18 and 19? So if we were to look at area 18, we would find area 18 somewhere over here. And then over here, you'll find it on both sides of area 17. That's 1, and that's 2. So those are your area 18. And finally, area 19 can also be seen on both the lateral side of the left side of the brain, as well as the medial side of the right side of the brain. Before we look at the different lesions that occur in the optic pathway, it's important to understand that the visual field has different respective areas. So, if we were to draw, let's say, so this right here is my left visual field, and this is my right visual field. We can divide this into 4 parts, including this central area, which is known as your macula. So we can divide it into 4 quadrants. How do we label these quadrants? Well, it's very simple. Everything on the lateral side is known as your temporal side. Hence, this side is also your temporal side. But this right here is your right temporal side, and this is your left temporal side. The area in the middle is known as your nasal field. So how can we divide this? We can divide this into right upper temporal, right lower temporal, right upper nasal, right lower nasal, with the macula in between. Similarly for the left eye. Left upper temporal, left lower temporal, left upper nasal, left lower nasal, with the macula in between. We're going to move on to the different types of damage that can occur in the optic pathway and how that can affect our vision. Well, coming back to our picture, here are a list of the optic pathway damages that we will try and cover. The first one is known as monocular vision loss. This occurs at the level of the optic nerve before the optic chiasm. So let's say, for example, if a lesion were to occur over here, we know that all the fibers coming in from the left eye will get blocked. Therefore, we will have complete loss of vision in our left eye. The second damage is known as the bitemporal heminopia. Bitemporal heminopia actually occurs at the level of the optic chiasm. Now, at the optic chiasm, it can be caused by a pituitary tumor. An enlargement can cause an impingement on the optic chiasm. Now, the only 2 fibers that cross from the optic chiasm are the temporal fields, aka the nasal retinal fibers. So in this condition, because the temporal field of the right eye and the temporal field of the left eye are being affected, blindness will only occur in the temporal sides. Third, we have a disorder known as contralateral homonymous hemianopia. Now, contralateral homonymous hemianopia occurs after the optic chiasm at the level of the optic tract. Now, it depends on which side of the tract is affected. So I'm going to be showing you both of them. So let's say, for example, the lesion occurs on this side of the tract. We know that from here, it's the temporal field of the right eye, but the nasal field of the left eye. So temporal field of the right eye and the nasal field of the left eye. And similarly, if we were to do the same thing on the other side, on the right side, then we can trace them back to the nasal field of the right side and the temporal field of the left side this time. So blindness would occur in this area. Now there's a very special condition. It is the same as this, but it occurs with something called macular sparing. Now, if you remember, I told you that the macula is an area that is rich in blood vessels. So sometimes in specific people, either they have a large macula or collateral blood supply to the macula. It causes the sparing of the macula. And I also told you that the macula is a central area. So if the lesion, let's say, for example, were to occur on the right side, but you have macular sparing, this is how it would look. Now, if you were to demonstrate that for the left lesion with macular sparing, it would look something like this. So that's right here is a better representation of how contralateral homonymous hemianopia occurs with macular sparing. Now, finally, you can have lesions on the Meyer's loop. You can have it on the left side, and you can have it on the right side. Now, this causes a condition known as contralateral superior quadrantopia. Depending on right or left, let's say, for example, the lesion occurs on the right Meyer's loop. We know, and if we can trace back, we can see that the right nasal field and the left temporal field are affected. Therefore, if we were to look at where the blindness occurs in this patient, it would be in the top left corner. Similarly, if the lesion were to occur at the left Meyer's loop, it would be in the top right corner.